Today we're going to be looking at the second derivative test. So in the last couple videos, we looked at the first derivative test and saw that it helps us figure out where our function is increasing and decreasing, and also where we have maximum and minimum values. The second derivative test is going to tell us about something called concavity. So what I mean by concavity is this. The easiest way to think about it is with a parabola. Say we have two different graphs here. One that's a parabola opening upwards, and one that's a parabola opening downwards. Okay, this first graph right here where we have this upward facing parabola, this would be considered concave up. And the second one where we have this downward facing parabola, this would be considered concave down. Now, in the case of a parabola, the entire graph is either concave up or concave down. But in a lot of different graphs, you're going to have different pieces, some of which are concave up and some of which are concave down. And this is where our second derivative test is going to come in. It's going to help us figure out where a function is concave up and where a function is concave down. Okay, so let's look at what this test tells us. Second derivative test. All right, so if f double prime of x, which is just the second derivative, is positive, then f of x is concave up. On the other hand, if f double prime of x, so again the second derivative, is negative, then f of x is concave down. Okay. The other thing we're going to need is one quick definition here, and that's something called an inflection point. So an inflection point is where the graph of f of x changes concavity. Okay, so where it changes from concave up to concave down or vice versa. These are going to occur where the second derivative is equal to 0. These will occur at points where the second derivative is equal to 0. Not necessarily every point where the second derivative is 0, but these are going to tell us our possible inflection points, and we're going to have to do a little bit of extra work to figure out if they actually are inflection points or not. All right, so let's look at a couple examples. All right, so we are going to find the open intervals on which the graph is concave up or concave down. All right, so let's start with a simple function. Say f of x is equal to x cubed. All right, so in order to apply our second derivative test, we're going to need to take the first derivative and then the second derivative. So this is just going to be a simple power rule. So our first derivative would simply be 3x squared. And then our second derivative, which just means we're taking the derivative again, would be 6x. Okay, so then we're looking for our possible inflection points. And these are going to be where that second derivative is equal to 0. In this case, it would just be at x equals 0. Okay. All right, so now to figure out A, if this is an inflection point, and then B, where it's concave up and where it's concave down, we're going to make a number line just like we did with our first derivative test. I'm going to make a little number line here, and I'm going to put 0, which is our possible inflection point, on that number line. And this creates two intervals around 0. So just like we did in the past, we're going to pick some test values within each interval, and we're going to plug those into our second derivative to see if it's positive or negative at that point. All right, so to the left of 0, I'm just going to go with -1, and to the right of 0, I'm going to go with +1. Okay, remember our second derivative function here is just 6x. So if we plug a -1 in there, we'll get -6. We plug a +1 in there, we'll get +6. All right, so this means that to the left of 0, our second derivative was negative. And according to our second derivative test back up here, if the second derivative is negative, then f of x is concave down. So on this interval, our function will be concave down, right? And then to the right of 0, we came up with a +6. And where our second derivative is positive, the function is concave up. Okay? So if we want to write this out as an interval, we would say our function is concave down on the interval -∞ to 0, and it's concave up on the interval 0 to infinity. Right, and if you just take a second to just think about the graph of this function, which I'm not actually asking us to do in this problem, but just to kind of think about it real quick. Our cubic function, which hopefully you remember what that looks like, and of course something like that, right? So if we think about our concavity here, we found our inflection point, okay, which 0 is in fact an inflection point. Because our graph changes concavity at that point, it goes from concave down to concave up. Right, so we have this inflection point right here at 0, and you can see by looking at this graph that this is facing downwards. So this is concave down right here on the left. We have our inflection point at 0, and then it's concave up after that point. So what we found with our second derivative test matches up with what we already know about that function. All right, so this is one example using our second derivative test. Let's go ahead and look at another one. Let's look at one that's a little bit more complicated this time. Let's try f of x is equal to 6 divided by x squared plus 3. All right, so again, to find our concavity, we need to find the second derivative. And on this function, we basically have two choices for how we want to go about finding our derivative. We could either use the quotient rule, since we're dealing with a fraction, or we could rewrite this function. Since we just have a constant in the numerator and not a variable, we could just rewrite this as 6 times the quantity x squared plus 3 all raised to the power of -1, and then it would become a chain rule problem. So I'm going to go about it this way and just use chain rule instead of quotient rule, but you could just as easily go quotient rule if you prefer. All right, so first, let's find our first derivative. All right, so chain rule here, start with the power rule. So we'll have a -6 out front after bringing that -1 out. Then the x squared plus 3. And then subtracting 1 from our exponent will give us a -2. And then chain rule, take the derivative of the inside, which would be a 2x. Okay, and then just cleaning this up a little bit, this would be a -12x times x squared plus 3 to the power of -2. All right, now I'm not going to bother rewriting this as a fraction just yet because we still need to take another derivative of this. So I'm going to leave my first derivative there, and I'm going to go now to my second derivative. So we're taking a derivative again, right? And this time, because we have the -12x times this quantity, we're going to have to use our product rule. All right, so product rule, we take the first times the derivative of the second. And again, we're going to have to use chain rule here. So pull that -2 out front, subtract 1 from our exponent, and then chain rule, multiply by the derivative of the inside, which would be a 2x. Okay, so remember we're still thinking product rule, so that was the first function times the derivative of the second function, and then plus the second function times the derivative of the first, and that would just be a -12. All right, now we definitely want to clean this up a bit before we try and do anything with it. So let's go ahead and just simplify this a little bit here. All right, so we have a -12x, we have a -2, and we have a 2x. So that would give us a 48x squared. And we still have that x squared plus 3 to the -3. And then minus 12 times x squared plus 3 to the -2. All right, now I'm going to change my negative exponents back to fractions. So we'd have 48x squared divided by x squared plus 3 quantity cubed, and then minus 12 over x squared plus 3 quantity squared. All right, now to simplify this further, I want to go ahead and put this all over a common denominator. So since this is x squared plus 3 quantity cubed, and this one's only a square, I'm going to go ahead and just multiply by another x squared plus 3 over here to get that common denominator. We'd have 48x squared minus 12 times the x squared plus 3 all over x squared plus 3 quantity cubed. All right, keep simplifying a little bit. So we'd have 48x squared minus 12x squared minus 36 all over x squared plus 3 quantity cubed. Combining like terms, 36x squared minus 36 all over x squared plus 3 quantity cubed. All right, now I'm going to go ahead and just factor that numerator. So I'm going to pull a 36 out of both terms. And then notice that the x squared minus 1 is a difference of squares. This will finally be 36 times x minus 1 times x plus 1 all over x squared plus 3 quantity cubed. Okay, so we finally have our second derivative all simplified. Okay, so now we're looking for our possible inflection points, which again means we're looking for where the second derivative is equal to 0. And when we have a fraction, that essentially just means where is our numerator equal to 0. So I'm going to set my numerator to 0, which gives us for our possible inflection points x equals 1 and x equals -1. Okay, so now to figure out where we have our function concave up and where it's concave down, we need to make our number line. All right, so I'll put the -1 and the +1 on the number line here. All right, and we need to pick some test values. So I'll go with -2, 0, and 2. And then we need to plug these into our second derivative. All right, didn't do this ahead of time this time, so I'm going to go ahead and punch these in. Let me type this in my calculator real quick here. All right. Just waiting on my calculator to load. Okay. All right, so if we plug in a -2, I got 108 over 343. I plug in a 0, I get -4 over 3. And if I plug in a 2, I get 108 over 343. Okay, so now looking at this, we can see that our intervals are positive, negative, and positive, which means our function will be concave up to the left of -1, concave down between -1 and +1, and concave up to the right of 1. So because our function is changing concavity at both of these points, these are inflection points. Okay. And let's write out our intervals. So it's concave up on the interval -∞ to -1, and then again on 1 to infinity. And it's concave down on the interval -1 to +1. All right, so that is the second derivative test. In the next video, we'll look at how we can apply this to curve sketching.